my subject is secular evolution of disks. When we see pictures of galaxies today, such as this one from the Hubble telescope, we have to understand the properties of the disk galaxy that we're looking at have two sources. They were disk galaxies were formed by some means which is currently the subject of a tremendous amount of research effort by the galaxy formation community. But those galaxies, after they formed, evolve internally, and to some extent the two processes happen concurrently. I would say in the first half of the universe, the formation part of the galaxy evolution was dominant, and in the second half of the evolution of the universe, the internal evolution is probably more important. And it has become clear that, that a lot of the internal evolution of galaxies has been driven by spiral activity, and this has only recently been understood. And if we're going to try to understand how spirals drive evolution, then we need to understand a little bit about the origin and why galaxies have spirals. Before I go on to the next slide, can you reassure me that that everybody is able to hear me and see what I'm presenting?
We can hear you well, and we see your presentation. Thank you.
All right, and if people wish to interrupt and ask questions, that is fine as I'm going along, because I've got time, I think. Now, as Mahmoud mentioned, we have a galaxy simulation code, which is highly efficient, and I'll talk about that in my other lecture later today. But what I'm presenting in this animation, which I hope you can see, is the evolution of a thin disk galaxy, which has been set up and is evolving under its own self-gravity, with just the application of Newton's laws of motion and gravity and very little else. The collective effects of a large number of particles, in this case 200 million particles, but that's not necessary to use that many every time. And the fact that you see spirals appear spontaneously in the simulation, it loops back and starts again as it is now, and here you see the spirals beginning. This shows that, proves to us that the physics of spirals is just that of gravity and inertia. But it has taken me a long time. People have been seeing spirals in simulations for over 50 years, or about that, and I have not been working in at simulations quite that long, but almost, and it's taken me most of my life to understand how this happens. Let me just spend a few minutes explaining what is going on. So what I'm showing you in this animation are estimates of the amount of power. These contours that you're looking at here are the amount of power that are in various Fourier modes of the disk. There is the red line in the top and bottom plots shows you the frequency at which the stars would co-rotate with the sorry, the circular angular frequency is a function of radius, and if you have a disturbance that is horizontal, a horizontal stripe, as you can see several of those, that indicates that there is a coherent wave of a fixed frequency that is present in the simulation for a short period of time. And the time that the m equals 3 harmonic is in the top, m equals 4 is at the lower panel. Both of them are evolving and both of them are producing structure. And to begin with, we look back to the beginning, most of the power is in the inner galaxy, and later on it moves to the outer galaxy, and then eventually dies away, as we saw in the movie of the formation of structure. And what I've understood from these information like this and other evidence, which I'll come to in a minute, is that each one of these horizontal stripes is separately a spiral mode, an instability of the system, which lasts somewhere around 10 orbits at its co-rotation radius. And as I said, it affects the inner disk at the beginning, and later on it spreads to the outer disk, and then finally the activity fades away because random motion has risen up. Now, most recently, I've really understood exactly how one spiral wave can excite another one. If you have a very simplified simulation in which you start with one pattern, and that one you seed the simulation with a single disturbance which has a certain angular frequency. The inner limb blood resonance would be where this dotted line is, the co-rotation resonance would be where this dashed line is, and the outer limb blood resonance would be where that line is. That instability, which I started the simulation, has evolved for some period of time, and after it's finished evolving, the structure of the density of particles in the space of the actions. This is radial action in the vertical direction and angular momentum or azimuthal action in the horizontal direction. The colors indicate that there have been changes to the density of particles in the space of these two actions, which suggests that resonance scattering has been an important part, and particularly at the inner resonance. But there are faint structures here at the outer resonance, and it was possible for me to prove that the inner resonance is already very close to the center of the disk, and it's not terribly interesting and not very important, not able to do much because the inner disk has already done a lot. But the outer limb blood resonance was able to seed a new instability, which allowed the system to develop a second spiral mode with co-rotation of that mode at the outer limb blood resonance of the first mode. And this is the way in which the spiral activity develops. And all of this is described in a somewhat technical paper that I wrote with Kullberg last year, Sellwood and Kullberg 19. And so each of the, what I'm saying is that each of those waves, coherent waves that we saw in the power spectrum, is a true unstable mode of the disk, but it's not an unstable mode of the disk as it began. It's an unstable mode of the disk as it has been modified by previous activity. And so those unstable modes grow until they saturate, then they rotate for a couple of rotations, and then they begin to decay. And as they decay, they scatter stars at the limb blood resonance, their limb blood resonances, which creates another modification to the disk, which seeds a new instability. And so the cycle becomes self-perpetuating. But unfortunately, as the cycle proceeds, there's a lot of random motion builds up in the disk, and it makes the cycle self-limiting. So if I start with a simulation that has and don't do anything about it, the heating continues for probably 20 or 30 rotations of the disk before the random motion of the disk becomes too large to support any more spirals, as we saw in my movie. But work I did many years ago also with Kullberg, back in '84, we were able to show quite convincingly that all you have to do is add some gas into the, mimic the effects of gas in the simulation in some way. We didn't actually do any hydrodynamics, but you mimic the effects of dissipation by creating new particles on nearly circular orbits, and that was we were able to keep the spiral activity going forever. All of that is old, and I wasn't going to dwell on that, but the mechanism for recurrence of spirals it was relatively recent, so I wanted to talk about that. Okay, now this is an important diagram. It's known as a limb blood diagram. if it's what I'm plotting here is angular momentum on the x-axis, energy of the stars on the y-axis, and co-rotation is the least amount of energy that a star can have at a given angular momentum, and that's this line here shows you where the circular orbit curve is. These are for stars which have the least amount of energy for their angular momentum. But it's perfectly possible to have stars on eccentric orbits with more energy than they need for a given angular momentum, and those eccentric orbits fill this area up in the top left-hand corner, and you can't, of course, have stars in this lower right-hand corner because they're energetically impossible. Now, when you have a rotating wave of disturbance of a particular pattern speed, there is Jacobi taught us many years ago an invariant which is the only conserved quantity in a rotating non-axis symmetric potential, which is causes changes in energy to be related to changes in angular momentum, and the proportionality constant is the pattern speed. And so if you're going to have any changes of any scattering that's taking place in the simulation, in this diagram, it will take place along a line of always having the same slope, which is omega p in this diagram. And you will see that in the co-rotation, or stars using pattern speed at co-rotation, oops, didn't mean to do that. Back. The scattering vectors are parallel to the circular orbit curve, and so if you exchange energy and angular momentum, these stars which change their energy or angular momentum stay roughly the same distance from the circular orbit curve, and you don't get any additional random motion. But both at the outer Lindblad and the inner Lindblad resonance, if you transport angular momentum outwards, these vectors point away from the circular orbit curve, which means that more random motion is being added to the system. And that energy is coming from the gravitational potential well of the galaxy, or extracting energy from the gravitational potential well by transporting angular momentum outwards. And you get no heating at co-rotation, but you do get heating at the Lindblad resonances. Now, one thing we know is that disk galaxies are generally, the stars in the disk are quite cool. They have random motions which are only a small fraction of the circular orbit speed, which is why the disk is thin and rotationally supported. But if you're going to have evolution of the galaxy over a long period of time, you can determine from the level of random motion that's present in the galaxy the amount of angular momentum redistribution that must have occurred amongst the stars at the Lindblad resonance. In fact, you can I have this formula in my review paper from a few years back now, which says that the change of angular momentum of a given part of the disk divided by that angular momentum, so the fractional change, is proportional to this group of terms here, and the sigma is the velocity dispersion of the stars in the disk, and v is the circular speed. So sigma over v is a small number, like around 10%, and then a is the size of an individual epicycle of the star would undergo, divided by the radius at which the star is orbiting, and so that is also a small fraction. So this is a small quantity twice. So this is typically around 1% or so of the amount of angular momentum in the distribution. And so this is telling us that although outward transfer of angular momentum from one inner part of the disk to the outer part is responsible for heating the disk, it actually is a relatively small change which produces as much heat as we see. And so the distribution of angular momentum within the disk is not changed by a large amount. It has to be changed because the energy has to be extracted from the potential, but that is not a particularly large change. But because, as we saw earlier, it was possible to have exchanges at co-rotation which do not cause random motion, then this particular bound applies only to the heating at Lindblad resonances, and we can have as much exchange of angular momentum at co-rotation as you want, and that will have no effect on the overall distribution of angular momentum. And I hope okay, that's probably better. You can now read the last line. Another difference between, this formula applies to the stars in the disk, because those are once they've been heated, there is no way that their random motion can be dissipated. But if you have gas present in the disk, then that can dissipate random energy, and of course that allows it to form stars on circular orbits. And so this constraint applies only to the stellar distribution, and the gas distribution can exchange much more angular momentum, and in fact it does. Now, I mentioned that the random motion in the disk rises as a result of spiral activity, and this is confirmed if we look at the Milky Way data. This is Makareth et al., who used Gaia data from the proper motions and estimated ages of the stars using apogee spectra. So this is very up-to-date new information here. And what they're showing here is the vertical velocity dispersion colored by age, estimated ages of the stars, and the radial velocity dispersion of the in-plane motion, again also colored by ages on the right-hand side. And although age is the principal color, variation it also varies with the metallicity of material. Old stars are much more metal poor than young ones. Now, this is consistent with the increase in random motion over time, so the older stars have more random motion than the younger stars, and therefore and this is consistent with the idea of heating by spirals. But I don't want you to run away with the idea that spirals are the only source of heating, because clouds and any debris that falls into the disk from outside can also stir up the disk and create some random motion. So spirals are not the only agent for heating the disk. And there is a relation here. You can see from the left-hand panel that the vertical velocity dispersion is smaller than the radial velocity dispersion, and that is generally true everywhere we look in the universe, in the disks that we can measure. And I will get back to explaining why there's a difference between those two towards the end of my talk. Let me move on to radial migration. This is a subject which came up in a paper I wrote with Binny back in 2002, and what I mentioned when we talked about the Lindblad diagram was that changes at co-rotation can be much greater than changes at the Lindblad resonances. And so once again, here is a diagram showing the change of angular momentum as a function of angular momentum. I hope you can see that. It's very faint, isn't it? Change of angular momentum in the vertical direction as a function of angular momentum in the horizontal direction as a result of a single spiral disturbance. So we were able to isolate a single spiral disturbance and show that this change of angular momentum was very substantial just across co-rotation. And there are roughly equal numbers of stars or particles in the simulation that gained angular momentum, therefore have positive delta L, and those that lost angular momentum, which have negative delta L. And so what is happening is that stars are just changing places across co-rotation. And for a long while, nobody really noticed that that was happening, because in simulations, all the particles are equal, and so it didn't really matter that particles were changing places across co-rotation, and nobody paid much attention to that. But of course, it's vitally important if those stars have different metallicities, because that means they move them around in the disk, and the fractional change in the angular momentum is actually quite large. You know, can be 2 out of 8, you know, 20% or something like that. And the mechanism for this is illustrated in this animation. I hope that you can see that. On the right-hand side here, you're looking at what's going on in the inertial wave. Imagine that there's a spiral density wave rotating around, and this particle, which began its life at the beginning of the animation, here it's just looped back to the beginning, began outside co-rotation, is being overtaken by the spiral because the spiral is going faster. And as the particle gets close to the ridgeline of the spiral, it gets turned back and moved inwards into an orbit that is inside co-rotation. And if it were to go all the way back around the galaxy and come back to the spiral again, of course it would be trapped. But when this motion is relatively slow, and by the time it gets all the way around the galaxy to the other spiral arm, that spiral arm has decayed, and so this produces an irreversible change in the angular momentum of the star. And the reason that stars get migrated is because the gravitational potential, the non-axisymmetric part of the gravitational potential, causes them to move uphill or downhill in the spiral density wave. And as they're moving slowly relative to the wave, the large changes in their angular momentum can build up, which causes the star to change its home radius by a big step as it crosses co-rotation. And that could be as much as 2 kiloparsecs in the case of the Milky Way. And as I said, the reason that this is not reversed is because by the time it gets to the second arm, if it lost angular momentum before, it would gain if the spiral was still there, but the spiral has decayed away, and so the change that it acquired at the one encounter with the wave persists. But we get new spirals arising all over the disk, as you saw in the earlier simulation. And so what this causes is the stars to random walk in radius, which leads to a diffusion of stars across the disk over time. That's been a very difficult prediction to find a definitive test. As far as I know, there isn't really yet a clear and definitive test which says, aha, this star was born at this radius, and we now see it at some other radius, and therefore we know it must have migrated. That is still beyond us. We haven't yet managed to devise a test that would confirm that this is exactly what is going on. But there's a lot of circumstantial or indirect evidence, and I'll just show one piece here. This panel on the left is data from the group in Sweden, Bensby et al. And what they're measuring is titanium, which is an alpha abundance element to iron, divided by iron to hydrogen. And they've separated the stars. This is a whole bunch of stars for which they have pretty high quality data. They separated them by their estimates of the age. And you can see that the younger stars form one trend and the older stars form a different trend. And the group in Australia, led by Van Hawthorne, Sharma et al., have created a model of a disk of the galaxy, which includes radial migration. And they are able to reproduce essentially the morphology of this structure in their model, and they claim, in fact, they show in their paper, that you can only get this double sequence, which is very clear in the data. You only get the double sequence if radial migration is included in the model. If they leave it out, then then you do not reproduce the distribution of elements, alpha elements. Although they chose titanium here, if you look back at their paper, there are other alpha elements, silicon and sulfur and others that they were measuring oxygen, which gave similar trends. All right, so radial migration. We also observe, when we look at galaxies, this is a collection of rotation curves from high quality 21 centimeter data by De Block et al. I've just chosen one, 3198 from their paper. And you see a smooth rise and a relatively flat, almost featureless part of the rotation curve. And this shape of the rotation curve has been remarked upon by many people as being remarkably featureless. You know, in the inner parts of the galaxy, this is supposed to be where the visible matter is important, and the outer parts of the galaxy where the dark matter is important. But there is no obvious feature in the transition from one component to the other. And people have called that a disk halo conspiracy of some kind. And then if you look at light profiles of galaxies, and this is work by Poland and Trujillo, they're plotting the estimates of the surface brightness of galaxies, seen in these images, as a function of radius on a log linear plot, and you see that the surface brightness decreases exponentially. And there are, in some cases, this one in particular pronounced, there is a break in the slope, but in between the surface brightness profile is very smooth. And it's not easy to imagine that hierarchical assembly of galaxies of the kind that people discuss, which is the constant mergers, infall of gas, and the stirring up of the system generally by this hierarchical assembly, would lead to smooth, featureless distributions of mass within and light within the galaxy. And so it's very hard to understand, or at least I would say it was hard to understand how that arises. And the answer, Berrier and I tried to provide an answer a few years back. We took a particularly pathological case of a galaxy with a dense bulge, a very low mass disk, and then a high mass halo, and then we tried to create a galaxy rotation curve and light distribution that was non-smooth by just constantly adding stars or particles at over some narrow range of radius. That was, we just deliberately try to do what we think might not be so unrealistic, which is to imagine a stream of gas falling onto the galaxy with some characteristic angular momentum and forming stars over a narrow range of angular momenta. How does that get distributed over the disk? And we found that even though we can constantly adding stars at the same radius, the mass distribution got spread out across the disk, so the surface density profile became smoother, and the rotation curve became flatter. And we observed that this was being driven by spiral evolution. A particularly vivid example in our paper is this one here. If you take a galaxy and you do not allow any non-axisymmetric forces to disturb the motion of the stars or particles in the disk, then as you add particles in the ring, they stay in the ring. There's nothing that can change their angular momentum. They stay there and the ring remains fixed. But the moment you allow non-axisymmetric forces to be present, then you find that the ring breaks up because there are strong spiral instabilities that are associated with this inhomogeneity. A non-smooth disk is very good at developing spiral instabilities, and those spiral instabilities spread the stars or particles across the disk. They give some of them a lot of angular momentum and move them outwards, some they take away angular momentum and move them inwards. And so even though we started with a rotation curve that was this funny S shape that you can see in the bottom right diagram here, By the time the simulation had finished, which was the magenta line, it was pretty nearly smooth. That's in this case here when the spirals were allowed. If you don't allow the spirals, you keep the gravitational field axisymmetric, then everything stayed unchanged. So these featureless disks that people observe, I think, are the result of spiral activity, which is very efficient at spreading the mass across the disk. And I said earlier that you don't get much angular momentum change to the overall distribution. This is one exception where where the changes are happening at co-rotation, and so stars are being moved away from this region here, away from large to large radii or to small radii, roughly equal numbers. So apart from it flattening the bump in the angular momentum distribution, this doesn't change the overall shape of the distribution at all, or much. There was a beautiful paper came out a couple of years after Berrier and I published, and I wish we thought of doing this, but it was obviously these guys were thinking hard about it, and they thought of they wrote this very nice paper where they showed that if you can assume that radial mixing is very efficient in disks, which I believe it is, then you can, with the constraints that mass and angular momentum have to be conserved, you can show that the maximum entropy state of the disk has the density distribution of angular momentum as a function of angular momentum. This quantity here has to be a rough exponential. Now, this is not quite saying the same thing as surface density, but what they're testing against is there was a paper back in '97 in which Courtauld showed the rotation curves of many galaxies and also the amount of mass that was present at each radius, the surface brightness profiles of those same galaxies. And using the data from that paper back in '97, they were able to show that almost all, well, in fact, their galaxies, all the information that they could get from galaxies was nicely represented by a single line in this plot here, which suggests that radial mixing is very efficient, and that produces relatively smooth light profiles and rotation curves. This doesn't on itself predict the light distribution should be exponential. It's the distribution as a function of angular momentum that should be exponential, but that can lead to an exponential-like appearance of the light distribution. Okay. Now, I mentioned earlier that if you look at stars in the solar neighborhood, you see that the radial velocity dispersion of the stars in the direction towards the galactic center or away from it is about twice as large as the velocity dispersion in the vertical direction. And but because if we imagine that a lot of the heating of the disk is a result of spiral activity, which I think it is, then because spirals have very large spatial extent in the plane, the stars that oscillate above and below the plane and do not get into resonance with the dense, the vertical motion doesn't get into resonance. The horizontal motions do. Horizontal motions produce Lindblad resonances, which produces heating, which we understand very well. But the vertical motions just don't resonate with the disturbance of the spiral pattern. So the only way that you can convert the random motion that the spiral pattern has created is to redirect those peculiar velocities of the stars by scattering from molecular clouds. And there's a beautiful paper by Ida et al. From the mid-90s, who are the only people to get this calculation right. And they were able to show that as a result of molecular clouds scattering, redirecting the star velocities, you would expect the radial velocity dispersion to be larger than the azimuthal dispersion and both of them to be larger than the vertical dispersion, and that's consistent with the observations. In fact, they were able to predict that for a flat rotation curve, the radial velocity dispersion should be about twice the vertical velocity dispersion. And that was just as a result of redirecting star velocities that ran by random scattering off of molecular clouds. Now, when you run a computer simulation, most computer simulations, the particle masses are very large. You can, if you run 1 million or even 10 million particles in your disk simulation, they're still much more massive than individual stars. So you need to get up to 10 to the 10 particles before you could get down to masses that are about the same as stars. And so you're running simulations with particles which are already quite heavy. And two-body relaxation is much more rapid in disk simulations than in spheres. This was something that's pointed out by Rybicki back in '72, but largely forgotten. And I reminded everybody about his paper in a paper in 2013. And these figures show what happens if I run a disk simulation with 10 to the 4, 10 to the 5, or 10 to the 6 particles. And I use two species, a heavy set of particles that are heavy and a set of particles that are light. The green particles are light, the heavy particles are red. And I'm showing the time evolution of the radial velocity dispersion, which is caused largely by scattering by spirals. But that's showing you that when you have a small number of particles, the heavy particles gain less energy than the light ones. So that's suggesting mass segregation, which is the result of something unphysical, which is that the simulations are suffering from two-body relaxation. It's worse because the vertical velocity dispersion differs more, this in the second column, by a larger amount than the radial velocity dispersion. And it's only when you get up to of order 1 million particles, this is 4 times 4 million, there's 2 million, I think it's 2 million heavy ones and 1 million, some number, I don't remember, some number of light ones and some number of heavy ones, mostly light, that produce this total number of 4 million. And the shape of the velocity ellipsoid, if you do the calculation right, should not change, because I don't have, in my simulations, I don't have molecular clouds. And so you should not see the vertical velocity dispersion rise as it does when you have small number of particles. And so if you run a simulation with a small number of particles, then you do get the right shape of the velocity ellipsoid, because the energy is exchanged between radial and vertical motion, but that's because of two bodies scattering between the stars and nothing to do with the molecular clouds, which are missing from your simulation. So it's kind of ironic that if you do a sloppy simulation, you get the right answer for the wrong reason. But people still don't understand that. How am I doing for time? Okay. So I'm going to finish up with just two other aspects of galaxy evolution, and that's disk halo interactions. Victor de Battista, who will speak to you later, was a student of mine many years ago, and his thesis was on dynamical friction on bars, and I don't think he's going to talk about that, so I'll say a little bit about his thesis work. And then another paper that I wrote with Berrier just a couple of years ago. So what de Battista showed was that if you have a bar in a disk that is rotating inside a halo of particles, that the rotation of the bar can transfer angular momentum from the bar and the disk to the halo. And since the bar is losing angular momentum, it slows down. And if you slow down a bar, that means that the co-rotation radius should move outwards in the disk. And the figure that I'm showing you here is a recent measurement from a group in Spain, the Khalifa sample of galaxies, where they've measured the co-rotation radius divided by the bar semi-major axis. This number is predicted to be close to 1 when bars form, but if they're subject to a lot of dynamical friction, then that number should rise to 1.5, 2, or maybe even more. And each one of these 4 panels is a slightly different measure of the same thing. But in their paper, they had 2 ways of measuring the bar length and 2 ways of measuring the co-rotation radius. And so that gave them 4 possible ways of calculating the ratio of co-rotation radius to bar semi-axis. But you can see that from the red dots that they are, which are their data, that most bars are lie down here around about 1, which means that co-rotation radius is only just outside the bar, the semi-major axis of the bar. The boxes and the grey points are other people's data that they culled from the literature, and this little offending box up here, it comes from some people who use spirals to try and estimate the co-rotation radius, which is a very dodgy way of trying to do that. So I don't think you should pay a lot of attention to those blue boxes. So the conclusion from de Baptiste's thesis was that the halo must have a low density, because if you've got a bar moving through effectively through honey, which is will slow it down, it will slow down rapidly, and the honey must have a very low density and be very inviscid if it's going to if the bar is going to survive as a fast bar, as we observe from these data and all the other data that have been collected. And this was a very awkward result for the galaxy formation people, because they wanted their halos to have high densities and the disk to have no mass. But de Battiste was quite insistent that the only way you could achieve this was if you have a heavy disk and a low density halo. And the people went after his result for numerical reasons over for years, but it stood up well, and it's now, I think, pretty much accepted. So that was good for him. He stuck to his guns and kept and got the result accepted. And one final thing, which really surprised me a few years back, was in this another project that I did with this guy Berrier. We have a rotation curve with a disk and a halo, and as we added the disk into the halo, we compressed the halo to take account of the fact that the gravitational potential was getting deeper as we were adding mass into it. So this was all done adiabatically in the adiabatic approximation without any simulation being done, but you can calculate how the halo should respond to the arrival of additional mass within the disk if that arrival is adiabatic. And so the blue line here is what you get if you compress the halo as a result of adding the disk. If you don't compress the halo properly, then you get the red curve. And in the bottom panel, we show what happens if you run the simulation of this disk galaxy model with some amount of random motion in the plane, and you use a rigid halo then you get this result for the bar amplitude given by the red line, which is almost nothing. The bar doesn't develop at all. But the moment that you allow the halo to have some to be represented by a live population of particles, you get the blue line, which shows that the amplitude of the bar rises and rises very amazingly, constantly for a long period of time. Therefore, it means that one of the things that Mahmoud has been interested in is trying to suppress bar instability by modified gravity, but bar instability is still a real problem for theorists working on galaxies, because we still don't understand how it is that if halos can excite the formation of a bar, how any of the galaxies that we see in the universe have no bar. And it's quite clear that some fraction of the galaxies have no bars. This green line is of another experiment that we did, where we said, all right, well, let's destroy the bar and see what happens if we just randomize those particles at this particular time and destroy the bar. But the bar begins to reform later. So that's not that was just a side issue. So the conclusion from this work is that disks in live halos can behave very differently from disks in rigid halos. And of course, if you want to have modified gravity, then you can do away with the live halo. So that might be an interesting idea. I'm going to stop now. I've just picked out a few of the highlights of some of the things I've worked on over the years, particularly as they relate to secular evolution. And it's clear that many properties of the disk galaxies today have resulted from substantial internal evolution, but there are still plenty of puzzles that we don't understand, this being one of them. And I'll stop here.